Okay, so radioactive decay, emission of radiations from unstable nuclei. So carbon-14, it is produced because of the cosmic rays which enter the atmosphere from outer space. Okay, so the neutrons, they hit this carbon-12 and make it, to change it into carbon-14. Okay, so this is one of the unstable isotope and it emits beta particles. Okay, so in the same way, like we cannot say about radioactive decay, there are few things. Like it is random. What does that mean? Random means if you have so many nuclei, okay, there are different atoms. You don't know which atom out of so many will emit radiation. Okay, we cannot say which atom or nucleus, because nucleus decays actually, okay, will decay now. Out of so many, say 1000 atoms or 1 lakh atoms are there. So which atom, this, which one will decay? Now we cannot say. Okay. In the same way, like this atom, we can also not say when will this particular atom decay. We call it randomness. Which atom right now, which one will be decaying out of so many? Or suppose if you start considering one, when will this decay? We cannot say. Okay, but we can say one thing, we call it randomness, random decay. One more thing is what? Spontaneous. Means we cannot affect the decay rate by pressure, heating, etc. Okay, when you heat up, the decay rate will not be affected. It's totally nuclear phenomena. In the same way, when you apply pressure on it, press it, apply humidity, pass current through this, if it is metallic atom, nothing will happen. Nothing will change its decay rate. Okay, but we can say one thing for sure. What we can say for sure? Out of so many atoms, half of the atom will decay in this period of time. Okay, suppose there are 10 million atoms. You can say it's not 10 million, it's 1 million atoms. Okay, so 1 million atoms are present. So we can say in this time, in particular time, 1 million means 10 lakhs. So in particular time, half of them will decay. Okay, and then in the same period of time, out of this means 2.5 will be decaying. Okay, half of this, half of 5 lakhs means 25, 2 lakhs 50,000. Okay, these will be decaying. I will take smaller number. It's a very big number. Suppose there are 1000 atoms. So in a particular time, say 2 days, 5 days, 20 days, half of this will decay. Means how many will be left? 500 atoms in suppose 10 days. Then in further 10 days, what is half of 5,500? 250 will remain and 250 atoms will decay in further 10 days. Then in further 10 days, half of this means 125 will remain and 125 will decay in further 10 days. So this we can say. Okay, so this number in which half of the atoms initially present decay is called half-life. Okay, so today we are studying actually about half-life of a radioactive element. Any sample has so many atoms. Okay, so half-life is the time in which half of the unstable nuclei initially present will decay. Decay. So this will be the half-life. Okay. So what does half-life, what does decay mean? Means suppose there are uranium atoms. Okay, there are 1000 uranium atom. In 10 days, what happens? This is an example. Okay, this is not the half-life of uranium. Every atom has its own half-life. Any unstable nuclei has its half-life period. Like carbon 14, you know, its half-life time is 5,300 years. Okay, some have iodine, 131. Its isotope of iodine, it has half-life of 8 days. Means in 8 days, half of the atoms initially present will decay. It means they will become something else. Daughter will be different. Okay, they won't be same element now. Okay, like carbon 14, it decays and it becomes nitrogen 15. Okay, so it means the atom will change its identity. So half of uranium atom, suppose they decay into neptunium. So 500 are uranium which are remained and 500 are neptunium, Np. This is uranium. Then in further 10 days, half of this 5,500 will decay. 250 will be uranium and 250 will be neptunium. Now what is the total of neptunium atom? 500 plus 250. So number of atoms which are decaying, it will keep on increasing, and undecayed which are remained, that will keep on decreasing. So for this purpose, we can have a table half-life. Okay. So suppose number of undecayed nuclei initially present is n. Okay, so we may assume n is, say, n is 10,000 atoms. Okay, the sample has 10,000 atom of particular element. Okay, maybe uranium, maybe iodine, maybe potassium, any. Okay, so after, and say it has half-life of, say, 10 days. Okay, say half-life is equal to 10 days. Every element has different half-life. It means 10 days, what will happen? They will remain n by 2. Now let me draw the table. Initially, how many are present? N. Okay, what will happen after one half-life? One half-life means 10 days. it will remain out of, say they are n is equal to 10,000. So what will happen after 10 days? 5,000 will remain and 5,000 will decay. Okay, so n is 10,000 initially. Okay, what will happen after one half-life? Half-life, number of half-lives. Fraction of atoms remain. I will give in terms of fraction. Fraction of atoms remain. Fraction decay in half-life. Okay, total decayed. Because total decade will keep on increasing. So when one half-life is passed, what will happen? And by 2 will remain, and by 2 will have decayed. And by 2 here in our example, and by 2 is 5,000. Okay? And 5,000 have decayed, and 5,000 are remained. So total which have decayed, because it's only one half-life, so that is only 5,000 in our example. Okay, now when two half-lives means 20 days. If one half-life is 10 days, means 20 half-lives will be, 20 days will be two half-lives. Okay, so 10 days, for example. So two half-lives means 20 days. So what will happen? What is half of n by 2? It will be n by 4 now. It means it is 2,500. Half of 5,000 is 2,500. Now, half of this have decayed also. N by 2. See. Okay, so after the time of two half-lives, n by 4 are remained. See, this is very important. Remain fraction is very important. Remain, and how many have decayed? Half of the previous one means n by 4. 2,500 are remained, 2,500 are decayed. So total decayed means if you add this to previous one, 5,000 plus 2,500 means 7,500. And in terms of fraction, 3 by 4 have decayed. Out of total n, 1 upon 4 are left and 3 upon 4 are decayed. Now, how many we have now? Leftovers are n by 4. 3 half-lives means 30 days. So half of now n by 4, because they were remained, means n by 8 will remain. Means if you take half of this, what will you get in 1250? See, so numbers are only assumptions. Okay, these many have decayed, n upon 8 have decayed, n upon 8 have left after out of n by 4. So what is total decayed? They were already there. Now we add. We keep on adding those. N by 8 to the fraction which have decayed after 3 half-lives means 30 days. We will add this. What do we get when we solve it? LCM is 8. So 7n by 8. Okay. So it means 7,500 plus 1250, which have decayed. So what is this total which have decayed now up till now out of this? 0, 5, 7, 8. Okay. So these have total decayed. See, the number which are decaying in 10 days, it is constantly decreasing. The decay rate, first, how many decayed in 10 days? 5,000. Then how many decayed in 10 days? 2,500. Then how many decayed in 10 days? 1,250. Okay, now 4 half-lives means 40 days. Half of this. Which were remained in the previous half-life? N by 8 were remained. So n upon 8 means n by 16 are remained and n by 16 have decayed. Half of the previous one. Half of the previous one, n by 8. What is half of n by 8? N by 16. They are remained and they are decayed. Means 625 you can say. So now add this n by 16 to previous one. Total decayed means n by 16 plus 7n upon 8. What is the total now? 615 n upon 16. Means if you add 625 to it, 0, 0, 9400. Have I added correctly? The 973. Okay. Three, 7, 5. They are remained now and they are totally decayed. They have become some other atom now. Decayed means they have changed their identity. From uranium, they might have become neptunium, or from any other iodine, they might have become something else. Okay. So now they see this is a very good relationship, one kind of thing. Some power of 2 is going on. N upon 4, n upon 2, n upon 4, n upon 8, n upon 16. What can you say about fifth half-life? Now you can guess. Not necessary. They not necessarily become stable. Okay. If those which are produced, the daughter ones, if they are also not stable, they will have their own half-life and they will start their own decay process. Okay. So that will be different story then. Okay. We are talking about now particular ones. Okay. What is remain and what is decayed. Decayed are separate. If they are also unstable, they will start their decay process and we will have to consider them separately. Okay. Now, so what can you guess? One very good, you can say, relationship is going on. You can make a link. What I'm doing here. You check, we go to the previous window. See, 1 half-life, half of n. 2 half-lives, n by 4. 3 half-lives. Let me do it on the other page. After 1 half-life, multiple of half. Yes, power 2. 1 half-life, 1. Okay. Remained. I'm talking about remained. Okay. 2 half-lives, 1 upon 4 means 1 upon 2 into 1 upon 2. 2 halves. You can say 1 upon 2 raised to the power 2. This. 3 half-life means 1 upon 8 means 1 upon 2 into 1 upon 2 into 1 upon 2. How many halves are there? As many half-lives are there. Means 1 upon 2 raised to the power 3. This is the fraction remained. This all is about fraction of atoms remained. Okay, 3 half-lives, 1 upon. What do we say about 4 half-lives? 1 upon 16 means 4 halves. So this power is equal to number of half-lives. So 5 half-lives means what do we have? 1 upon 2 raised to the power 5 means 5 halves. Means 1 upon 32. 6 half-lives, 1 upon 64 means 1 upon 2 raised to the power 6. So if I ask what fraction of radioactive active atoms remain after 5 half-lives, what will you say? 1 upon 2 raised to the power 5 of n. N is any number of atoms, like we assume 10,000. Okay, so it means what fraction remains? 1 upon 32 n. Okay, and what have decayed? Subtract 1 upon 32 from n. N is the total initially present, and n upon 32 are remained. So what is decayed? You will get 31 upon 32. Let us go to this previous window and let us see it again. See, the fraction total decayed and remained. See, this is n upon 2, n upon 2. Check this. N upon 4, 3n upon 4. 1 less in the numerator. N upon 8 remained, 7 upon 8 n decayed. N upon 16 remained after 4 half-lives, 15 upon 16 decayed total. N upon 32 remained after 5 half-lives, 31 upon 32 decayed after 5 half-lives. Let me resume. We can have a formula. What fraction, number of atoms or fraction of atom remained after n half-life. N can be 1, 2, 3, 4, 5. Okay, n half-lives. What is equal to fraction of atom remained? You can simply write remained. N half-life means 1 upon 2 raised to the power n into n. Okay, where n is number of half-lives. Like if I say a given sample has say 16 into 10 to the power 9 atoms of iodine 131. How many are remained after say 128 days, or okay, half-life of iodine is 8 days. Iodine 131 is 8 days. So in 128 days, how many half-lives have passed? You can get number of half-lives is equal to total time divided by time of one half-life. If you divide total time 128 days by 8, 8 is one half-lifetime, time of one half-life. You will get number of half-lives. So here total time is 128. When we divide this by 8, what do we get? 16 half-lives. No, I think I did something wrong. Let me check. No, correct. 16 half-lives have gone. I will make the number smaller instead of giving 128 days. It has to be not 120, I did something wrong here. Let me make it 64 days. So in 64 days, how many half-lives would have gone? 8 half-lives. Because 16 will be very big number. So we will get very small quantity. So I'm just giving what? 64 days. So 64 divided by 8, 8 half-lives. So we can solve it by putting in this 1 upon 2 raised to the power 8 into what was initially present, 16 into 10 to the power 9. So we'll get the number remained. Okay, so can you solve this? How many are remained? Can you solve this?